Can you imagine stepping foot on a world orbiting another star within your lifetime? Scientists at Caltech have developed a microscopic sail that could be propelled by lasers to speeds approaching 20% of light speed, fast enough to reach Alpha Centauri in just 20 years. The physics behind this technology seemed impossible just a decade ago. Today, I'll explore how these laser-driven light sails work and why they represent our best shot at interstellar travel. From theoretical concepts to groundbreaking experiments, we'll trace the remarkable journey of how humanity's oldest form of propulsion is being reimagined to potentially carry us to the stars. From Kepler to Caltech, the 400-year journey. The story of light sails begins not with modern technology, but with a remarkable astronomical observation over 4 centuries ago. In 1610, while studying the night sky, Johannes Kepler noticed something peculiar about comets. Their tails always pointed away from the sun, regardless of their direction of travel. This seemingly simple observation led him to an extraordinary hypothesis. In a letter to Galileo Galilei, Kepler proposed that the sun must be exerting some kind of pressure, that sunlight itself might be pushing the comet tails away. This was a revolutionary idea. In an era when the nature of light was still deeply mysterious, Kepler intuited that light might possess physical force, that photons, though massless, could somehow transfer momentum. He even speculated this force might one day be harnessed for travel, writing about ships or sails adapted to the heavenly breezes that might carry explorers through the cosmos. Yet Kepler's insight remained dormant, a seed planted in scientific soil that would take centuries to germinate. The 17th century lacked both the theoretical framework and the experimental capability to confirm whether light truly exerted pressure. For over 200 years, this intriguing hypothesis lay waiting, overshadowed by more immediately practical astronomical questions. The scientific foundation finally began to take shape in the 1860s when James Clerk Maxwell developed his groundbreaking equations of electromagnetism. Maxwell's work mathematically demonstrated that light consists of electromagnetic waves and, crucially, that these waves carry momentum. His equations predicted that when light reflects off a surface, it transfers twice its momentum, providing the first theoretical confirmation of Kepler's observation. Still, the amount of pressure exerted by light is extraordinarily small. Maxwell calculated that sunlight at Earth's distance exerts just 4.7 micropascals, a force so minuscule that if you placed a postage stamp in space, sunlight would take centuries to push it the length of a football field. This seemingly impractical force led many to dismiss light-driven spacecraft as fantasy. Experimental confirmation came in 1900 when Russian physicist Pyotr Lebedev and American researchers Ernest Nichols and Gordon Hull independently measured this tiny force using torsion balances with reflective vanes in vacuum chambers. Their work validated Maxwell's predictions and opened the door to practical applications. The Soviet physicist Friedrich Zander formally proposed solar sailing for spaceflight in 1924. His calculations revealed light pressure's key advantage, persistence. Unlike chemical rockets that burn briefly, light pressure continues indefinitely, allowing gradual acceleration to potentially enormous speeds. Progress moved slowly over the decades. The Soviet Union's Xenomya experiments in the 1970s deployed large reflective films in orbit, demonstrating that ultra-thin reflective structures could function in space. NASA developed several designs, including a half-kilometer square sail for a Halley's Comet mission, though budget constraints repeatedly delayed practical demonstrations. The first real breakthroughs came in 2010. NASA's NanoSail D successfully deployed a 10-square-meter sail in Earth orbit, while the Japanese Aerospace Exploration Agency, JAXA, achieved an even greater milestone with Icaros, the interplanetary kitecraft accelerated by radiation of the sun. This spacecraft deployed a 14-meter diagonal square sail and became the first to demonstrate controlled solar sailing in interplanetary space during its journey to Venus, proving the technology's viability. These missions highlighted a fundamental limitation. Sunlight's diffuse nature produces extremely slow acceleration. Icarus achieved a velocity change of just 400 meters per second over 6 months, impressive for zero fuel consumption, but inadequate for interstellar travel. This limitation prompted a conceptual leap. If natural sunlight provides minimal acceleration, what about concentrated artificial light? By directing powerful lasers at a light sail, the pressure could be thousands or millions of times greater. The concept of laser-driven light sails emerged as a potential solution to the interstellar travel problem. Physicist Robert Forward's calculations in the 1980s suggested gigawatt-power lasers could accelerate small spacecraft to a significant fraction of light speed, potentially enabling missions to nearby star systems within a human lifetime. The concept remained theoretical until advances in laser technology, nanomaterials, and miniaturized electronics began to make such missions increasingly feasible. This convergence of technologies attracted serious attention in 2016, when Russian entrepreneur Yuri Milner established the breakthrough Starshot initiative with $100 million in initial funding. The project aims to develop technology to send gram-scale spacecraft with light sails to Alpha Centauri at 20% of light speed, completing the 4.3 light-year journey in just over 20 years. Central to realizing this vision are experiments at Caltech, where researchers have created nanoscale light sails that function as scientific instruments. These silicon nitride membranes, just 50 nanometers thick, allow scientists to precisely measure the forces exerted by laser light, providing the experimental foundation needed for practical spacecraft. The Caltech work represents the culmination of a 400-year scientific journey from Kepler's initial observation to practical laboratory demonstration. These tiny vibrating membranes are the direct descendants of Kepler's heavenly sails, transformed from philosophical speculation to experimental reality. The historical arc from Kepler to Caltech illustrates a common pattern in scientific progress. Observation leads to theoretical insight, which awaits technological capability to test and apply. Kepler could observe and hypothesize, Maxwell could mathematically prove, and now modern scientists can measure and harness light pressure for practical purposes. This connection across centuries reminds us that scientific progress isn't always linear or predictable. Ideas can lie dormant for generations before emerging as transformative technologies. What seemed like an impractical curiosity, the minute pressure of light, may ultimately provide our best hope for becoming an interstellar species. The microscopic trampoline revolution. At the Kavli Nanoscience Institute at Caltech, a material 700 times thinner than a sheet of paper is demonstrating precisely how light can push matter. This microscopic trampoline, measuring just 40 microns on each side, could be the key that unlocks humanity's path to the stars. The structure itself defies intuition. Imagine something smaller than the width of a human hair, yet capable of withstanding the forces needed for scientific measurement and eventually space travel. This silicon nitride membrane stretches just 50 nanometers thick, so thin that if you were to look at it edge on, you'd need an electron microscope to see it at all. What makes this experimental platform revolutionary is its dual functionality. The membrane serves as both a prototype light sail and a precise scientific instrument. This microscopic square sheet, suspended at its corners by silicon nitride springs, creates what researchers describe as a resonator, a structure that vibrates at specific frequencies when disturbed, much like a finely tuned violin string responding to the slightest touch. When laser light strikes this suspended membrane, something remarkable happens. The photons, despite having no mass, transfer momentum to the material. This causes the membrane to vibrate in measurable ways, allowing scientists to detect exactly how much force the light exerts. It's a breakthrough that transforms centuries of theoretical understanding into tangible, measurable data. The engineering challenge behind creating such a structure is considerable. The material must satisfy two seemingly contradictory requirements. It must be incredibly thin to be responsive to the minute pressure of light, yet strong enough not to immediately disintegrate under that same force. Silicon nitride emerged as the ideal candidate for this application. This ceramic compound exhibits exceptional mechanical properties, maintaining structural integrity even when fabricated into films just tens of nanometers thick. Its tensile strength allows it to withstand the stress of being suspended and the repeated vibrations induced by laser light without breaking. The team achieves geometric precision through electron beam lithography, which creates structures with nanometer-scale resolution. The process transforms a silicon wafer coated with silicon nitride into the delicate membrane structure, precisely controlling its dimensions and properties. When researchers first observed the membrane responding to light pressure, the lab erupted in excitement. They were witnessing the direct conversion of light into mechanical motion at a scale never before achieved. The membrane's corners are anchored by silicon nitride springs that work like tiny suspension systems. These springs allow the membrane to move in response to light pressure while maintaining its overall position and shape. When photons strike the reflective surface, they impart momentum that causes the membrane to vibrate in specific, measurable patterns. These vibrations occur in multiple modes, side to side, up and down, and rotational movements, each providing different information about the forces being applied. By using optical techniques to monitor these tiny movements, researchers can measure displacement smaller than the diameter of an atom. This measurement capability represents a scientific breakthrough. The membrane effectively transforms the invisible pressure of photons into mechanical motion that can be observed and analyzed, similar to how a drum's surface reveals sound waves through its vibrations. The implications extend far beyond the laboratory. By understanding exactly how light interacts with these ultra-thin materials, engineers can begin designing full-scale light sails with confidence in their performance. Questions previously answered only through mathematical models can now be tested experimentally. How does the material's reflectivity affect momentum transfer? What happens when the angle of incident light changes? How do different wavelengths interact with various sail materials? These experiments allow researchers to study material behavior under conditions that approximate actual space missions. While scaled down dramatically, the physical principles remain the same. The forces experienced by the 40-micron membrane under laboratory laser light mirror those that would affect a meter-scale light sail propelled by a powerful laser array. The measurement precision achieved with these vibrating membranes is astonishing. Forces as small as a few pekinewtons, equivalent to about 1/1,000,000th the weight of an apple, can be detected. This sensitivity is essential because even though light pressure is minuscule, it's exactly this force that would accumulate over time to accelerate a spacecraft to unprecedented speeds. One of the most promising aspects of this research is its scalability. The physics demonstrated at this microscopic scale can be directly applied to larger structures. The membrane serves as a proof of concept for the underlying principles that would govern light sails of any size. As researchers perfect the membrane's composition and structure, parallel work continues on power delivery systems, spacecraft miniaturization, and navigation techniques. Each element must advance together for light sail technology to become viable for actual missions. What's particularly exciting about Caltech's approach is its transformation of theoretical physics into practical engineering. By creating a platform that both demonstrates and measures light pressure, researchers have bridged the gap between physics textbooks and space mission design. These ultra-sensitive membranes could potentially serve as advanced scientific instruments, detecting minute gravitational variations, measuring radiation pressure, or serving as extraordinarily sensitive microphones for faint signals. For space exploration, the implications are profound. Traditional rocket propulsion fundamentally limits our ability to reach distant targets quickly because of the rocket equation's tyranny. More fuel requires more structural mass, which needs even more fuel. Light sails offer a pathway around this limitation. With no propellant to carry, they can theoretically accelerate continuously as long as they remain in the laser beam's path, reaching velocities that conventional rockets could never achieve, measuring the unmeasurable force detection breakthroughs. The rocket equation creates a fundamental limit for traditional propulsion, but light sails offer a potential workaround if we can accurately measure their effectiveness. Scientists faced an extraordinary challenge. How do you detect and quantify forces so minuscule they operate at the picometer scale, that's trillionths of a meter, yet could theoretically accelerate spacecraft to unprecedented velocities? This measurement challenge represents one of the most significant hurdles in light sail development. For decades, scientists operated largely on theoretical models rather than empirical data, because the forces involved, photons striking reflective surfaces, produce effects almost impossibly small to detect with conventional instruments. Traditional force sensors simply lack the sensitivity required to measure radiation pressure accurately, creating a scientific blind spot that has hindered practical engineering applications. The measurement problem becomes even more complicated when you consider that any instrument sensitive enough to detect these forces would likely be affected by numerous confounding factors: thermal fluctuations, gravitational variations, electromagnetic interference, and even quantum effects could all mask or distort the tiny signal scientists are trying to isolate. Imagine trying to balance a feather on a razor's edge. During an earthquake, that's the level of precision researchers needed to achieve. Caltech's breakthrough approach solved this problem through an elegant dual-purpose design. Rather than treating the light sail and measurement apparatus as separate systems, it integrated them into a single platform. The nanoscale silicon nitride membrane serves simultaneously as both a prototype light sail and an extraordinarily sensitive force detection instrument. To achieve this remarkable sensitivity, the research team built a custom vacuum chamber housing the microscopic sail and incorporated a sophisticated interferometer into their microscope system. This setup allows them to detect movements as small as picometers, a scale so tiny that a single hydrogen atom has a diameter of about 100 picometers, meaning these researchers can measure displacements smaller than atomic dimensions. Interferometers work by splitting light into two paths and then recombining them, creating interference patterns that change with incredibly small movements. When the laser strikes the membrane, causing it to vibrate, these vibrations alter the interference pattern in ways that can be precisely measured. This allows researchers to quantify exactly how much the sail moves when struck by light, essentially measuring the force of light itself. This measurement approach can detect both linear and rotational movements with remarkable precision. When light strikes the sail off-center, it creates a torque that causes the membrane to rotate slightly. The platform measures these rotations precisely, providing critical data about how light sails would behave in space, where maintaining proper orientation relative to the propelling laser beam is essential. The mechanical stiffness of the membrane, how much the springs deform when pushed by the laser's radiation pressure, represents another critical parameter. By carefully measuring the stiffness, researchers can determine exactly how much force the laser exerts on different sail materials and designs. This allows for direct comparisons between theoretical predictions and actual measured performance, bridging the gap between physics equations and engineering reality. Consider the implications of this measurement capability. Engineers can systematically test different materials surface treatments and geometric designs with unprecedented precision. Rather than relying solely on theoretical models or macro-scale approximations, they can directly measure how nanoscale variations affect performance. Does a specific pattern of nanoscale ridges improve reflection efficiency? Does a particular material composition reduce absorption? These questions can now be answered empirically. The research setup's ability to measure side-to-side motion holds particular significance for future light sail applications. In space, a sail that drifts sideways out of a laser beam would lose propulsion. The Caltech platform allows engineers to study these lateral movements and develop self-correcting sail designs that would automatically maintain alignment with the driving laser beam, a critical requirement for any practical interstellar propulsion system. This measurement breakthrough transforms light sail development from a largely theoretical exercise into an evidence-based engineering discipline. Each potential design modification can now be tested, measured, and quantified. The data generated allows for iterative improvements based on empirical results rather than theoretical predictions alone. Scientists can now confidently state the specific force generated by a particular design when struck by a given laser power. The vacuum chamber environment is another essential component of the measurement system. In normal atmospheric conditions, air molecules would interfere with both the sail's movement and the measurement process. By conducting experiments in a vacuum, researchers can isolate the pure effects of light pressure without atmospheric contamination, closely mimicking the conditions a light sail would experience in space. This measurement platform creates a critical feedback loop between theoretical physics and practical engineering. When actual measurements diverge from theoretical predictions, as they inevitably do in cutting-edge research, physicists gain insights about phenomena they hadn't fully accounted for in their models. These insights lead to refined theories, which in turn guide new engineering approaches, accelerating the development cycle. For full-scale light sail development, these measurement capabilities address several critical challenges. Engineers must determine optimal sail thickness, thin enough to minimize mass, but thick enough to maintain structural integrity. They must quantify exactly how different materials reflect versus absorb laser energy, as even minimal absorption could lead to catastrophic heating. They must understand how sail geometry affects stability during acceleration. All these questions can now be addressed with unprecedented precision. The ability to measure picometer-scale movements also enables researchers to identify potential failure modes before they become catastrophic, such as detecting resonant vibrations that could cause structural damage. What makes this measurement breakthrough particularly remarkable is that it required solving two extraordinarily difficult problems simultaneously, creating a material thin enough to be demonstrably propelled by light, and developing a system sensitive enough to measure the resulting movement. The Caltech team's success in addressing both challenges represents one of the most significant advancements in light sail technology to date, from stars to planets, shifting mission objectives. As engineers perfected these impossibly sensitive measurements, they discovered something unexpected about light sail potential. The technology designed to reach Alpha Centauri might actually revolutionize exploration much closer to home. This surprising pivot in mission planning has scientists reconsidering the immediate applications of what was once viewed primarily as interstellar technology. When breakthrough Starshot launched with $100 million in initial funding, it aimed to send gram-scale Starship spacecraft to Alpha Centauri at 20% of light speed, completing the 4.3 light-year journey in just over 2 decades instead of tens of thousands of years. Like a rocket engineer designing an intercontinental missile who realizes the same technology could power efficient passenger aircraft, scientists discovered their interstellar designs had immediate practical applications within our own solar system.